All right, welcome. We're going over section 9.3, the complex plane and DeMoivre's theorem. If I'm not pronouncing that right, I apologize. I never took French. Okay, so complex numbers, if you remember, they're written as a plus bi. A is the real part, b is the imaginary part of this complex number. So complex numbers, we can take them from a one-dimensional number into a two-dimensional complex plane. And instead of saying a plus bi, we're going to call them x plus yi, okay? So the x-axis will be our real axis. The y-axis is the imaginary axis. Okay, so let's take a look at this. How does this work? If I wanted to plot z such that it's the square root of 3 minus I, well, the x part, so there's my x value, is square root of 3. The y value is negative 1. So if I wanted to plot these, and let's say 1, 2, 3, 4. I'm just going to say 4 of these represent 1 unit. So the square root of 3 is approximately 1.7. So there's 1.5, approximate right there. That is where z would be located. Z is at square root of 3 minus I. Okay, so that's not too groundbreaking, right? So now the magnitude of this is going to be defined. We use the same bars we used with vectors. The magnitude is the square root of x squared plus y squared. So if this point is x plus yi right here, so this is my x distance, that's my y, the magnitude of that is x squared plus y squared square rooted. So that's just Pythagorean theorem. We're good with that. Now the conjugate, remember when we had conjugates, when we were trying to get rid of square roots in the denominator or i's, the imaginary part, you'd multiply by the conjugate. The conjugate was the same thing, but you changed the sign of the middle or of the second term. So now we're asked to multiply z by its conjugate. So I'm looking at what is z times its conjugate, and we put this bar on top of it to show this a conjugate. So what we're looking at is if I multiplied x plus yi times x minus yi, what do I get here? Okay, so let's go ahead and do that. We've got to do our distribution, so FOIL. So I get x times x is x squared, x times negative yi is negative xyi, positive yi times x, and then positive yi times negative yi. It's going to be negative y squared I squared. And we notice these cancel out, so we've got x squared minus y squared. But I squared, recall by definition, I is the square root of negative 1. So I squared is negative 1. So we get x squared plus y squared. So when we multiply complex number by its conjugate, we just get x squared plus y squared. Thus, the magnitude of z is simply what we have here, the square root of x squared plus y squared. Okay, let's move on here then. Okay, sorry, let's come back to this for a second here. So we know that the magnitude is equal to the square root of this, so we can also say that is equal to our square root of z times the magnitude, z times z conjugate. So either one of these gives us the same value, and we will use both of them. So let's turn this over to converting a complex number between rectangular and polar forms. I know, how are we going to do polar with complex numbers? So Keep in mind our radius for these have to be greater than or equal to 0, and the angle theta has to be between 0 and 2 pi, not inclusive of the 2 pi. So a complex number x plus yi may be written in polar form as the x value is going to be from r times the cosine of theta. Y part is r times sine of theta I. And we can put those together if we want. So radius times cosine theta plus I times the sine of theta. And let's take a look at this just so we see how that happens. So here is our triangle, if you will. Remember that if I were looking at this angle theta, the sine of theta is the opposite, y over the radius. Multiplied both sides by r, and we would have r times sine of theta. Those would cancel. And then if I wanted y by its r, that would give me y equals r times the sine of theta. Likewise, if I had cosine of theta equals x, so adjacent side over the hypotenuse, which is r, multiplied both sides by r, and those cancel, giving me that x equals r times cosine of theta. So just as a reminder where this comes from and where that comes from. Okay, and the magnitude now of this complex number z is simply the radius. So hopefully we can see how that happens. Okay, and now let's take a look. We want to write this expression of z is the square root of 3 minus I, and I want to write it in polar form. Okay, so that tells me the x value is the square root of 3. The y component is negative 1. Okay, so let's take a look at this. Well, positive x, negative y's got to be in this quadrant. So I'm dealing with something that looks like right there is z. This is negative 1. This is the square root of 3. If I need to find, there's my angle theta. And my radius right here, so radius, the radius is negative 1 squared plus square root of 3 squared, and all of that square rooted. So radius equals 1 plus 3 is 4, square rooted, that is just 2. So my radius equals 2. If I'm trying to find this angle now, well, let's see. So the sine of this angle, sine of theta, is going to be negative 1 over 2. Cosine of theta is adjacent side, so square root of 3 over 2. So what is the angle that has these two values? Theta must equal 11 pi over 6. And again, that's coming from my unit circle. So now I can rewrite this. So z equals square root of 3 minus I. If I rewrite it using this formula, oops, where'd it go? Radius times cosine of theta plus I sine of theta. So the radius we said was 2 times the cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. And there we go. We have now written that in polar form. Okay, how about this? We want to plot the point of z in the complex plane and write it in rectangular form. Okay, so let's plot the point. My radius, looking at this, radius is 2, theta is 30. Well, a positive radius, which it has to be by definition, and our angle of 30 is in the first quadrant. So there is z. There we go. The radius is 2. If I want to now write this in rectangular form, this is z is going to equal 2 times, well, not, it does equal, plus I times the sine of 30. So if I want to convert this to rectangular form now, what is the cosine of 30 degrees? That is the square root of 3 over 2 plus I times the sine of 30 is 1/2. So now I've got to distribute this 2 to both of these terms. So I get 2 square root of 3 over 2 plus 2 over 2I. And all I did is move the I to this side so it's in proper format. And let's simplify it. We get the square root of 3 plus I. So that is in rectangular form. This was in polar form. Okay? So again, we're just using this formula up here. This is our rectangular form, and this is our polar form. So we have some theorems now of how we can combine two different complex numbers. So here we go. So I've got Z1 and Z2. So if I have these two different complex numbers, then if I multiply them together, here's how I can write the answer in polar form. Provided that the second complex number is not 0, or the second complex number is not equal to 0, then I can divide them, and here's how I would get the answer. So let's try this. I've got Z is 4 times cosine of 35 plus I times the sine of 35, and W is 2 times cosine 80 plus I sine of 80. I want to find Z times W. So I'm just using this formula. I'm plugging in the values. So the radius here times this radius, so that's 4 times 2 times the cosine of the first angle, cosine of 35 degrees plus the second angle, so that's 80 degrees, plus I times the sine of the first angle plus the second angle. And let's try and simplify that. So 4 times 2 is 8 times cosine 35 plus 80 is 115 degrees plus I times the sine of 115 degrees. That wasn't so bad, was it? So that is now in my polar form, and that is Z times W. Okay, this next one, sorry, I didn't give myself enough room here. Z divided by W, again, I'm just using the formula. So I take the first radius divided by the second radius, so this equals 4 divided by 2, multiplied by the cosine of the first angle, so that's 35, minus the second angle, so that's 80, plus I times the sine of 35 minus 80. Okay, and we want to simplify this. We are told we're going to be leaving it in polar form, so that's great. So 4 divided by 2 is 2 times the cosine of 35 minus 80 gives me negative 45 plus I times the sine of negative 45. That's all well and good. However, keep in mind our angle has to be between 0 and 2 pi. So these angles of negative 45 degrees, I need to convert. They're in the correct location, but I need something that's coterminal with them. So I'm going to add the one period, so 360 degrees to each of those. So I still have 2 cosine. 360 plus 45 gives me 315 degrees. Plus I times the sine. Same thing here. I've got to add 360 degrees. So that gives me 315 degrees. So that was plus 360, plus 360. Because it'll have the same sine value and same cosine value, but it just meets the criteria that we're limited to theta being between 0 and 2 pi. So now that is in polar form. That's Z times W, and this one is Z divided by W. Okay, let's try another one. So I'm given two complex numbers in polar form, and I want to multiply them. So let's try this one. And I encourage you to try these yourself first, and then check yourself. Z divided by, or Z times W, 3 times 5 times the cosine, and we add the two angles together, 20 plus 100, plus I times the sine of 20 plus 100 degrees. Okay, so 3 times 5 is 15, times the cosine of 120 degrees, plus I times the sine of 120 degrees. That is in polar form. So we are all done with that part of it. Second part here, z divided by w. Again, we're just following the formula. So the first radius, 3 divided by 5, times the cosine of 20 minus 100, plus I times the sine of 20 minus 100. I was already calculating what that was. We have 3 over 5. Cosine 20 minus 100 is negative 80 degrees, plus I times the sine of negative 80 degrees. And again, I can't have negative angles, so to get rid of the negative angles, I am going to add 360. So I have 3/5 times the cosine, negative 80 plus, that doesn't look like a 360, plus 360 is 280 degrees, plus I times the sine of 280 degrees. And there we go. Okay, let's continue on. I'm glad you're sticking with me for this. Okay, let's hope I do not massacre pronunciation here. DeMoivre's theorem. DeMoivre's theorem is basically useful because it allows us to find roots of complex numbers. We've been able to add them, subtract them, multiply, and divide, but we've never been able to find roots. DeMoivre allows us to do this. This was in the early 1700s. He came up with this. So let's take a look at how we do this. So z, again, that's your complex number to the nth power, is equal to the radius to whatever the nth power is, times the cosine of n times your angle, plus I sine of n times the angle. So let's see what we can do here. So I'm given this. So here is my complex number written in polar form raised to the fourth power. I want to write it as a plus bi. Okay, so this is going to equal, again, I'm just going to use this formula. The radius is 2 to the nth power, that's 4. So 2 to the fourth power times the cosine of n, that's 4, times my angle, so times 15, plus I times the sine of 4 times 15. And now we just want to simplify this. Okay, 2 to the fourth power is 16. This is cosine of 4 times 15, that's 60 degrees, plus I sine of 60 degrees. Okay, well, I want it in standard form, so I need to put what the actual value is here. So the cosine of 60 degrees is 1/2. Plus, I guess I didn't really need that parentheses, 1/2 plus I, what is the sine of 60 degrees? It's the square root of 3 over 2. So now I'm just going to distribute. 16 times 1/2 is 8. 16 times the square root of 3 divided by 2 is going to be 8 square root of 3 times I. And I now have converted this to the form of a plus bi. Okay, I have taken this and raised it to the fourth power. Okay, let's take another one. So I'm going to take this one, and again, I want to write it in that form. So my R value is 2, the N value is 3. So try this yourself and then check back to see if you did it correctly. 2 to the third times the cosine of 3 times 20 plus I times the sine of 3 times 20. That gives me 8 cosine of 60 degrees plus I times the sine of 60 degrees. Put in those values. Cosine of 60 is 1/2 plus square root of 3 over 2 times I. And the I should go after the real part of the number. I did not do that correctly there. And distribute. 8 times 1/2 is 4. 8 times square root of 3 over 2 is 4 square root of 3 times I. Okay, so far so good. Look at this one. This one is given to me in standard format for a complex number, and I want to raise it to the 6th power. Well, I certainly could go through and do 2 plus 2i times 2 plus 2i. That answer times another 2 plus 2i, it's going to get really old. I don't want to do that. So if I could write this in polar format, then I could just use my formula. So need polar format. So first thing I need to do is let's take a look at what we're dealing with. 2 plus 2i. So 1, 2, 1, 2. It's right there. Now notice that if I go the exact same distance here and the exact same distance there, what kind of angle must this be when your x value and your y are the same? That angle, theta, has got to be 45 degrees. And we've seen that enough times, hopefully, that you're comfortable with that. So this was 2, this was 2. If I wanted to know the radius right here, which we do need to know, so the magnitude, that is equal to, radius is equal to x squared plus y squared square rooted. So that is, 2 squared plus 2 squared square rooted, or in other words, the square root of 8, which is 2 square root of 2. Okay, we're almost there. Hang in there. We can get through this. So we now have my radius. That's your radius. We know the angle. I can now write this in polar form. Okay, we've got our radius. We've got our angle. So now I can write this piece of it, 2 plus 2i, can be written as 2 square root of 2 cosine. And I could do that either in degrees or radians. So I'm going to go ahead and do radians here, just because, plus I times the sine of pi over 4. You can use either one. It's not going to change our answers here whatsoever. Okay, but I want to take this and raise it to the 6th power. So my n value is 6. The radius is 2 square root of 2. So 2 plus 2i to the 6th power. I take my radius, 2 square root of 2, and I have to raise it to that power, to 6, times cosine. 45 degrees would have been easier to use, so let's put the 45 here. So 6 times 45 plus I times sine of 6 times 45. We just don't have to mess with any fractions then. Okay, so here we go. So now I want to take this and raise it to the 6th power. So 2 to the 6th power and square root of 2 to the 6th power. So 2 to the 6th power and square root of 2 to the 6th power is going to give us 512. Okay. And 6 times 45 is 270. So this is the cosine of 270 degrees plus I times the sine of 270 degrees. Okay, let's just substitute in our values here, and we're almost done with this one. 512 times cosine of 270 is 0. Look at that. Plus I times the sine, I don't want sine, I want the actual value. That is a -1. So what we get, 512 times 0 is just 0. And we can write the 0, and then 512 times negative I is negative 512I. So you can write it like this, or you can leave off that imaginary part. And that is in the form of A plus BI. Let's do another practice one like this. And again, go ahead and give this a shot yourselves, and then unpause this and come back to it. So 1 plus I to the fifth, we are plus 1 plus 1. So again, same magnitude in each direction, 1 and 1. So I know I'm dealing with a 45-degree angle, and I need my radius. My radius is going to be 1 squared plus 1 squared square rooted. So that is the square root of 2. I feel like we see this number a lot, don't we? So now if I want to write this 1 plus I in polar form, it's going to be the radius, the square root of 2, multiplied by this guy, or written in normal form. So I could write, and this is the square root of 2. So this is going to be the cosine of this. So the cosine of that, we're just going to call this pi over 4. I'll go ahead and just use radius, or radians versus degrees, plus I times the sine of pi over 4. There we go. And now what I'm really looking for is 1 plus I to the fifth power. So I take the radius, square root of 2, and raising it to the fifth power, times the cosine of 5 times pi over 4, plus I sine of 5 times pi over 4. Okay, so 2 to the fifth, 2, 4, 8, 16, 32. That's the square root of 32. So I'm going to have to simplify that. Times the cosine of 5 pi over 4 plus I sine of 5 pi over 4. Let's just put in these values. Simplify 32. Well, the square root of 32 is the square root of 16 times the square root of 2, 4 square root of 2. Cosine of 5 pi over 2 is negative square root of 2 over 2 plus I times a negative square root of 2 over 2. And we want to distribute this. This is getting messy, isn't it? So 4 and 2, well, let's go ahead and multiply this out. So this is going to give me negative 4 square root of 4 over 2 minus 4 square root of 4 over 2I. And then let's just simplify. So square root of 4 is 2. 2 times 4 is 8. Divided by 2 is just the 4. And it's still negative. So this is negative 4I. There we go. We have now written this raised to the fifth power this way. And our final part here, we've gone from this and raised it to a power. We can go the opposite direction and take the roots now, which is, again, the real goal here, is that I can, if I have z, so some complex number, I can find, and k represents what type of root I want. Like a 2 would be a square root, etc. But I can find these roots. So let's work an example here. There's a lot of stuff, but let's see how this works. Final problem, hang in here. So I've got negative 1 plus square root of 3i. I need this again in polar form for this to work. So my radius is going to, let's just go ahead and sketch this. So negative 1 positive, so somewhere over here. And this is negative 1. This is the square root of 3. So my radius is going to be negative 1 squared plus square root of 3 squared, all of that square rooted. So radius is 1 squared is 1, square root of 3 squared is 3, that's 4, square rooted is 2. My radius is 2. Okay, awesome. We've got that. Good, good, good. Now we want to take a look and let's figure out what theta is. So for right here, the sine of theta is opposite over adjacent, or over hypotenuse, square root of 3 over 2. The cosine of theta is negative 1 over 2. Well, the angle, this implies theta must be 120 degrees. Or if you want to do this in radians, that is the same as 120, so 2 pi over 3. Whichever one you want to use is fine. I'm going to use this in degrees for this problem. So let's work through now, and I'm going to plug into this equation. So I want z of k, that's going to be equal to find the common cube root there. So cube root is our k is 3. So I want the cube root of the radius, so that's 2, times the cosine of theta. Theta is 120 divided by n, so that I'm looking for the cube root. So that's going to be a 3. I'm looking there, that's a 3. Plus 2 times 3. Oops, I switched to pies in when I was doing 360 times 3. 360k. I'm sorry, k. Ugh. Let me back up here. Yeah, so up here where we have the 2 pi, we could also be using 360. So remember, 2 pi is equal to 360. So 360k divided by 3 plus I sine of 120 divided by 3 plus 2 plus 360k divided by 3. So again, I want to stick with degrees here. Okay, so we have the cube root of 2 times the cosine. 120 divided by 3 is 40 degrees, plus 120 degrees k, plus I times the sine of 40 plus 120 times k. Remember, when we were, oops, sorry, I went off the screen for you. K represents some integer. Now, if I wanted to find these roots, z sub 0, this was z sub k, the 0 root is going to be 3 square root of 2. So I'm just choosing different values for k right now. This was generic right here. Here I'm choosing specific. So wherever there's a k, I'm putting a 0. So cosine, this is just going to be 40 degrees because 0 times 120 is 0 plus I sine of 40 degrees. If I want the second, so that's one of the cube roots of this. The second cube root, I put a 1 in here. So I'm going to have cube root of 2 times the cosine of 40 plus 120 times 1 is 120 plus I times the sine of 40 plus 120. Or in other words, the cube root of 2 times cosine of 160 degrees plus sine of 160 degrees. And my third root, my third cube root here, oops, that's a 2. So we've got the cube root of 2 again, times the cosine of 40 plus 120 times 2, plus I times the sine of 40 plus 120 times 2. And let's simplify that. We have the cube root of 2. And notice all of these stay the same radius, times the cosine. 240 plus 40 is 280. So cosine of 280 degrees plus I times the sine of 280 degrees. And if we were to plot all three of these roots, so this one, and this one, they all are going to be a same distance from the origin. First one is in the angle of 40 degrees. Second one was 160 degrees. And the last one was 280 degrees. They are all equal distance apart here. But here's where one root is, here's the second, and here's the third root. So the angles between my roots are going to be the same, and they're all equal distance from the center. And that is DeMoivre's theorem. Good luck. I know this is a lot, but you can do it.